video, we're going to look at the violations of those Hardy-Weinberg assumptions that we can look at. We're going to look at changes in population size. So like what happens if we reduce population size? Population size are much smaller. We'll look at what happens if we have immigration coming into the population, if we have mutation, if we have non-random mating, and if we have selection. And there's lots of different kinds of selection. We'll look at some, and you will explore directional selection on your own later on. So let's look at, we're going to start out with an allele frequency of 0.5, just so it's in the middle. We can see changes easily. We're going to put the dominance deviation at 0, and we're going to put in a little bit of environmental variability. So if you remember from earlier when we looked at about Hardy-Weinberg, we expect that if the allele frequency, population size is big, the fluctuations in allele frequency over time are going to be relatively small. There's going to be some just because it's not an infinite population size, but if we run this for a few generations, you'll see that it fluctuates a little bit around 0.5. Let's run it for 10. And so now let's see what happens if we reduce the population size down and do set up at 10 individuals. What do we see happening here? You can see that it's fluctuating up and down at a much more extreme level. Even though it ends up back at 0.5, it switched to 0.35 and so on down the line, and so there's a lot more fluctuation. If we do this, you can run it again and you'll get a completely different scenario where it drops all the way down to 0.05 in that one. And then it actually went, the A1 allele went extinct after 8 generations. So you can see that the changes are random and can be quite dramatic if we have a small population size. Let's go back. If we throw in migration, let's just throw in some individuals for migration, and we can, if we put individuals in, we can alter the allele frequency of the migrants. So if you go to one of the extremes, like A1 at A1 is 0, meaning all the individuals that would enter would be A2, or you could go to the other extreme, and so that all the individuals that enter are A1. We can then look at this. If we hit go, what would go from a population size 1,000 to 1,040, and all 40 of those individuals are added to the A1 class. And if you were to test this for Hardy-Weinberg expectations, it would probably differ, because now we've got a totally different expectation here. The numbers are off in terms of what we would expect with the allele frequency of 0.95. You also notice that, not surprisingly, when we'll increase the allele frequency of the A1 allele when we add 40 individuals, so we're into it. So that's basically, you can play around with that a little bit more if you want to. Let's get rid of migration. Mutation, on the other hand, mutation are usually, we expect them to be approximately for any, like 1 in a million. And so we made this mutation rate a little bit lower. It's like 1 in 1,000, just so you can see something possibly going on. But if we go to our setup menu again and hit go, what we see is that nobody mutated in that generation. If we hit go again, we've got no mutation again. So you can see it's relatively low. Here we've got see if we can find one that we can get a mutation happening here. And here we go, finally. So that in this case, we had an individual that was a heterozygote and would have been A1, A2, and one of the alleles in that individual then mutated to an A2. So now we've gone from this individual here and added to this. So this one individual that was A1, A2, one allele mutated to produce A2 individuals. So now we've got that change. You can imagine that this is not going to have any effect on Hardy-Weinberg expectations. So mutation is not obviously, you can make your decisions about that. So what happens with, let's throw on non-random mating here. Let's hit setup. So the one thing about a mating is going to occur in the third situation, because this is basically what's going on within the population of adults, and then they're going to breed and produce the next one. So let's turn non-random mating. Let's put that on and hit go. So now we've got this one looks exactly the same because nothing is going on here. But in this case, what you're going to see is that we've now, because of the non-random mating in this case, that individuals that are similar down here are going to mate, and these individuals are going to mate. So it's positive assortative mating. If we want to see what happens, you can easily look at, we can put update plots here to see what it looks like. I can just show you really quick to see what happens afterwards. So now notice that the heterozygotes are decreased in number, which is what you would expect. But then if we hit another, if we turn this off, right, we'll just hit go again. Basically, it's going to go right back up to our essentially what we had before. So it returns fairly quickly to that. And then the last thing we want to look through here is selection. Selection is a little bit more complicated. There are 4 types of selection, the 2 types of directional selection. The greater than means that it will select individuals to the right side, or bigger individuals will be selected against. If it's negative, less than, then it's going to be smaller individuals are selected again. Disruptive selection is going to select the 2 ends or the 2 extremes and against the middle. And a stabilizing selection, we're going to select for the middle against the extremes. So depending on what, let's just look at disruptive selection really quick. And then there's going to be a selection range, and this is going to decide on what individuals are going to die in the population. So in directional selection, if you had greater than, then it would select against all these individuals here, and less than, it would select all these individuals on this side of that phenotypic value. If you're doing disruptive or stabilizing selection, it's going to be an absolute range, where disruptive selection is going to select all the individuals in the middle between minus 1.1 and plus 1.1, so it's going to remove both of those. And stabilizing selection will hit the end, so it'll anything less than 1.1 or greater than 1.1, less than minus 1.1 or greater than 1.1. Then the other thing that you can throw into the selection one is to lessen it. What this will do is, the way it's set up here, is that everybody dies that's outside that range. But if you throw in a probability of random death, that changes it so that some individuals that would be selected against will survive, and some proportion of those individuals that are selected for will die. And so it lowers the selection coefficient so that it's not as extreme. It's not basically, it's either you die or you don't die. There's some probability in between. So you can play around with that and how that works. So what we would expect that, let's look at disruptive selection here, and let's just make our range about here. So this means that anybody less than 0.7, minus 0.7, or anybody greater than plus 0.7 will survive. It's going to kill off, we should expect it to kill off the middle. And there's no probability of random death, so let's do that. So let's just see what happens here. If we hit go, let's hit setup, and then we'll hit go. So basically what we did was just it's going to kill off all those individuals in the middle. We go from a population size of 1,000 to a population size of 517, and we killed off all of the heterozygotes in the population. Let me just show you what happens if we throw in some random death. Let's just throw in a 15% thing, and we'll hit setup again, and we'll hit go. Now you'll notice that not all of the heterozygotes die. We'll get some differences, and not all of the homozygotes on the two ends will survive. So there's a range there that will go. If we get rid of selection, right, and then hit go again, then it goes right back to Hardy-Weinberg expectations again. We would see that. So those are some of the things you play around with on that.